Bismillah ar-Rahman ar-Rahim. This is the third video lecture in pharmacology for third year students. I'm Dr. Abdalrahim. Last time we were talking about NMR spectroscopy and discussing the factors which affect the chemical shift of different proton signals. Also, the proton NMR spectrum is associated with certain phenomenon called spin-spin coupling or spin splitting. That rarely ever the proton signals occur as singlets, but they are observed as doublets or triplets or multiplets. This is because the protons adjacent carbon are aware of the spin condition of each other. For example, if we have two carbons attached to each other, the protons in carbon A that are affected by the spin condition of proton on carbon B. For example, proton on A will recognize the upward and downward spin condition of proton on carbon B. And the signal of this proton will be observed as a doublet signal. Because every line in this doublet corresponding to a spin condition of the proton on carbon B. The distance between lines is called coupling constant and is given in hertz. It should be equal for coupled protons. This means that the proton, the carbon B, will be also split, or its signal will be split in the same way by proton on carbon A. This kind of coupling is called vicinal coupling, and the coupling information is transmitted via bond electrons. Hydrogen and adjacent carbon do not couple. For example, the protons separated by more than 3 bonds do not show this coupling phenomenon. This is called Pascal triangle. It describes the multiplicity of proton signals based on the number of protons in adjacent carbon. For example, in case of single signals, these are present on carbons which are not adjacent to proton-bearing carbons. The relationship here is the number of lines is equal to 2Ni plus 1, where N is the number of protons adjacent carbon, I is spin quantum number, and plus 1. If there is no protons on the adjacent carbon, it will be singlet. If there is one, it will the number of lines will be 1 plus 1 will be doublet in this case, and so on. We have different forms of multiplets, doublets, triplets, quartets, quintets, sextets, septet, octet, nonet, based on the number of protons in adjacent carbon to this proton. This is called proton multiplicity. The relative intensity of these lines is determined by the spin arrangements. The coupling constant. The coupling constant is the distance between the lines of a simple multiplet. The distance between lines of a simple multiplet. Its value is given in hertz. It is independent on applied field, in contrast to the chemical shift value in hertz, which depend on the applied radio frequency field. This is the NMR spectrum of ethyl group, for example, in ethyl iodide. The triplet signal here is for the methyl group, the methyl group in the ethyl. And this for the methylene. This is methyl because it's adjacent to 2 protons in methylene carbon. And this is quartet because it's adjacent to 3 protons on the methyl group. The distance between any two lines is called J. For example, we have here 3 J's and here 2 J's. And it should be equal, as we said before, for groups of coupled protons. The J value ranges from 0 to 18 Hertz, and its value provides structural clues. Its value provides structural clues. In case of unsaturated systems, there are additional coupling constants, values that we can report here. For example, in case of olefinic double bond, we have 3 types of coupling constants. The J3HH and the 3-bond coupling constant can be cis or trans. For example, here the J3AB is a vicinal cis coupling constant ranges from 6 to 11 Hertz, whereas the J3HC is a trans, J3 trans coupling constant. As you can observe, the trans coupling constant is more than the J3 cis coupling constant. This means that the coupling constant has structural or can determine the configuration of the double bond, whether cis or trans. An additional coupling constant for the 2 protons on the same carbon, B and C. This is a geminal coupling constant, J2 coupling or geminal, because 2 bonds are separating these 2 protons, and its amount or its value is small, from 0 to 3 Hertz. The proton or the J3 coupling constant in case of cyclic structure or cyclic olefins is affected by the ring size. For example, in the cyclohexene, the J3 coupling constant from 9 to 11 Hertz, whereas in cyclopentene, its value ranges from 5 to 7 Hertz. A long-range coupling is also observed for unsaturated systems because the pi electrons of these unsaturated systems provides coupling information for protons which are separated by more than 3 bonds. You can observe, for example, in allyl group, J4 coupling between proton A and proton B and C. These are separated by 4 bonds because of the presence of the double bond. Its form, its value is small, from 0 to 3 Hertz, but it is considered long-range coupling. Long-range coupling is also observed in case of aromatic compounds. You can observe, for example, in benzene type structures, ortho, meta, and para coupling. In ortho coupling, we have vicinal coupling, 2H and 3 bond coupling, and in meta oriented protons, we have meta coupling or J4 coupling. And here we have J5. 5 bonds are separating the 2 protons. The value of the coupling constant decreases by an increase of the number of bonds separating these protons. The splitting pattern of aromatic protons provides structural clues to the type of substitution on the aromatic ring. Integration is also an important phenomenon associating the proton-NMR spectrum, and it can be used to count the relative number of different nuclei for each signal. The height of the integration line is directly proportional to the area of the signal. The electronic integrators can provide, therefore, very important information about the number of protons present in each segment. For example, in the spectrum of benzyl acetate. And this structure or this spectrum, you can observe the chemical shift scale here in delta scale. We have 3 signals. The most of the shielded signals belong to 5 aromatic protons. This one in the middle for the methylene protons, and this one for methyl group. The integration line here, and you can see the height of this integration line, this height is 32 squares, whereas this is 22 and this one is 55. The ratio becomes 3 to 2 to 5, the same like the ratio of the number of protons. Here we have 3 protons, here we have 2, we have 5 aromatic protons. The effect of groups on the chemical shift is prevalent in this spectrum. You can observe that aromatic protons resonate downfield at about 7.3 or something because of the ring currents of the aromatic ring. The methylene group experience de-shielding from the O and from the aromatic ring, and this signal of the methyl group is upfield because it is least de-shielded. Conformation and stoichiometry in NMR. NMR is not a chiral technique. However, in some instances, chirality may have an influence on the chemical shift of protons. For example, methylene protons usually are equivalent and do not appear as or show different signals unless they are placed in a achiral environment, like for example, the compound is dissolved in chiral NMR solvent or optically active NMR solvent. However, if we have a methylene group adjacent to a chiral center, the 2 methylene protons are no longer equivalent, and they are or display different chemical shift, different coupling constant, and they couple to each other. In this case, they are called diastereomeric or diastereotropic protons. In the first case, they are called enantiomeric or enantiotropic protons. For example, in case of 2-chloro-2-phenyl-butane, the student is asked to draw this structure and figure out how the methylene protons in this case are different. Groups also can be inequivalent if they are present in a carbon adjacent to a chiral center. They are in this case also called diastereomeric or diastereotropic groups, like in case of 3-methyl-2-butanol. 2 methyl groups in this case are also not equivalent. Here the structure, 3-methyl-2-butanol. The 2 methyl groups on the 3 position, these 2 methyl groups are adjacent to carbon 2, which is not, which is the chiral center. Therefore, the 2 methyl groups, these 2 methyl groups are not equivalent. They have different chemical shift and different coupling characteristics. This is depicted here. These are the diastereomeric groups, and this is the stereo center. The spectrum of this compound can be described here. The signals here can be assigned as the signals NV2 doublets due to the 2 inequivalent methyl groups. Each one is a doublet, but doublet overlap with each other. They are if they are equivalent, they should have exhibited doublet signal only. One doublet signal due to coupling with this proton. However, we have 2 doublets here because each one is individually coupled to this proton. This is also a methyl group signal. It's also doublet due to this methyl group. This multiple signal is due to this proton, which is experiencing coupling with two different or inequivalent methyl groups. This singlet is due to hydroxyl proton, which can be further confirmed by D2O exchange experiment or deuteration experiment. The signal downfield here is due to this proton here, which is coupled with this proton and with this methyl group. The integration line, as you can observe, the proportion of the height of integration line can be justified by the relative number of protons. Here we have one proton, here three protons, and here are 6 protons. The ratio exactly matches the number of protons on each group. Spin decoupling or double resonance. In this experiment, in our experiment, we use an additional radio frequency. This additional radio frequency irradiates a selected group of coupled nuclei, causing them to undergo rapid transition among their nuclear spin states. This rapid transition upward and downward decouple the protons of this group from any spin interactions. This experiment is aiming at simplifying NMR spectra and assigning groups which are located in vicinity of each other, like the spectrum, for example, of propyl bromide. And this spectrum of propyl bromide, the chemical shift, as you can see here, for the different protons as due to their proximity to bromine, the electronegative bromine. The alpha protons on the alpha carbon to bromine is mostly shielded, followed by this methylene, by this methyl group, because bromine, as I said before, is an electronegative halogen. If we and this multiplicity of the signals is explained on the basis of the number of protons adjacent to the carbon they are located on. For example, this methyl group appears as triplet because it's adjacent to methylene group, triplet. This one is multiplet because it is coupling to methylene and to methyl group. This one is triplet because adjacent to methylene protons. If we irradiate the methylene protons alpha, the beta methylene will signal will collapse into a quartet because it's adjacent to 3 protons of this methyl group. Also, this one is not affected. If we irradiate the beta methylene group, the decoupling will simplify the signals of the alpha and the gamma groups into 2 singlets. So if we irradiate the methyl group, we will have 2 triplets due to decoupling between 2 adjacent methylene group protons. Carbon-13 NMR, very valuable type of NMR spectroscopy. As you know, carbon-12 is not in NMR chromophore. It has no nuclear spin. Nuclear spin I is equal to 0 because it has even mass and even atomic number. It was lately developed after proton NMR because carbon-13 NMR is a dilute spin. Its natural abundance is about 1%. Natural abundance of carbon-13 is 1%. The major isotope of carbon is C12. Also, carbon-13 has low magnetic moment, about 1/4 the magnetic moment of a proton. These 2 factors renders carbon-13 NMR 6,000 times weaker than proton in NMR spectroscopy. However, by the development of high magnetic fields up to 900 megahertz, 900 megahertz machine radio frequency and 21 Tesla magnetic fields allowed that we can observe carbon-13 NMR signals. The most useful information provided by carbon-13 NMR spectroscopy is the chemical shift value. Integration is not reliable in carbon-13 NMR because of different relaxation times of different types of carbons. We have methyl, we have methylene, we have methine carbons. Each one has different relaxation times. The higher the number of the protons on a carbon, the more it is enhanced, or its signal is enhanced. Therefore, integration is not a reliable parameter in carbon-13 NMR. Carbon coupling is very low probability because of the low natural abundance. The opportunity or the chance that we observe carbon-carbon coupling is 1 in 10,000 because the probability of a carbon to be 13 is 1%, natural abundance 1%. To have two C13s in vicinity to each other is 1 in 10,000. This is very low probability to undergo coupling or to show coupling. Carbon-13 NMR scale is very wide, ranging from 0 to 220, in contrast to proton NMR, which scale is spans 12 ppm almost. In absence of the coupling field, the carbon signals appear split by the protons that they carry. For example, the methyl will become quartet, methylene triplet, methine doublet, quaternary singlet. According to the n+1 rule we explained before, because carbon is also has a nuclear spin of half. Germinal coupling is very difficult to observe also here, and it has very low coupling constant. The vicinal coupling constant the one bond coupling constant in carbon NMR differ according to the hybridization condition of the orbitals or the carbon star. For example, in case of sp3 carbon, the coupling constant will be 125 Hertz, whereas in olefinic carbon it will be 160 Hertz, and in case of triple bond carbons it will be 240 Hertz. Therefore, the J value here gives the information about the hybridization of orbitals. As we said, carbon NMR spectra, in absence of the coupling field, we will have signals which are split by the protons present in each carbon. In order to get simplified in NMR spectra, we perform some decoupling experiments. For example, broadband decoupling or noise decoupling, proton noise decoupling, or community decoupling. In this experiment, we use a strong decoupling field of 300 megahertz. This cancels all coupling between proton and carbon, and all signals will appear as singlet signals. The number of these singlet signals matches the number of carbons in the compound in absence of equivalence. This is called a double resonance experiment because we are using an additional decoupling field in addition to the original radio frequency field. It also leads to enhancement of the carbon singlet signals due to NOA. The amount of enhancement depends on the number of decoupled protons. For example, the CH3 group will undergo enhancement more than the CH2 will undergo enhancement than CH group. Quaternary carbons is not affected because it has no protons. The second experiment is called SFORD, or single frequency of resonance decoupling. This experiment is used to determine the carbon multiplicity or the type of carbon, whether it's methyl, methylene, or methine carbon or quaternary carbon, called SFORD experiment. It uses also a strong decoupling field, but it allows one bond coupling so that the methyl group will appear as quartet, the methane triplet, the methine as doublet, and the quaternary as single. Another experiment in mass spectroscopy that can be performed to envisage the multiplicity of carbon is called distortionless enhancement by polarization transfer, or DIPT experiment. This DIPT experiment is one-dimensional anomalous spectroscopy technique which involves use of a series of programmed radio frequency pulses in both H1 and carbon-14 nuclei in this sample. It allows the detection of protonated carbons only. The quaternary carbons are not observed in this kind of experiment. The methyl and methine carbons will appear oppositely phased from the methylene carbon. Whereas while the methyl and the methylene, methyl and the methine carbons will appear upward, the methylene carbons will point downward. Spectral editing technique for anomalous spectroscopy, in which we can obtain separate spectra for each type of carbon. Spectrum for the methyl, spectrum for the methylene, spectrum for the methine. You obtain in this case what's called as subspectra. As I said before, quaternary carbons are not observed because they lack attached proton, and also the signal of deuterated solvents such as deuterochloroform, for example. The signal of this deuterated solvent is used in anomalous spectroscopy is not observed because of the lack of attached proton. This is a comparison of different types of carbon anomalous spectra for this compound, cyclopropyl methyl ketone. This compound has 4 types of carbons, and you can see here 4 signals. This signal, for example, is a triplet signal. Triplet signal is attributed to the methyl, the methylene, 2 methylene groups of the cyclopropyl ring because they are equivalent. The doublet here to the CH, the methyl group signal, in which the carbon is spread by 3 protons, is quartet. This single signal is due to the carbonyl group. This called of resonance decoupling. Here, completely coupled. This spectrum is a DIPT experiment in which the methyl groups and the methine appear upward and methylene group appear downward. And no quaternary carbon is there. Also here you can observe that in this spectrum, this is called completely decoupled spectrum. The number of signals here matches the number of carbons in the compound. And all the signals in the completely decoupled spectrum appear as singles. By running all the spectra, we can determine the carbon types comprising any natural product. Shielding characteristic and the characteristic capable shield of carbon-16 normal. The carbon-16 normal spectra or chemical shift range for carbon-13 is broad, spans more than 200 ppm, طبعا in proton NMR spectrum we have the scale about 10 ppm. Therefore, we said before that the signal overlap is difficult in this case. The chemical shift in the compositing NMR spectra is affected by the same factors operating in proton NMR spectroscopy, associated by electronegativity, hybridization, and anisotropy effects. The carbon-14 NMR spectra allow determination of number of different carbons in a molecule and equivalences or symmetry. For example, in this table. In this table here, we can predict the number of signals for each compound. For benzene, for example, you have one line, one signal because of equivalence. All the carbons are equivalent. One signal will appear. In case of chlorobenzene, we have 3 or 4 signals: ipso, carbon, ortho, meta, para carbon. In dichlorobenzene, we have ipso, ortho, meta carbon, 3 types, and so on. And the student is asked to be trained to predict the number of carbons in carbon-14 NMR, or carbon signals in carbon-14 NMR spectra of these compounds. The table shown in this slide provides information about how the chemical shift of the carbon atoms is affected by electronegativity, by hybridization of orbitals, and by magnetic anisotropy. For example, here we have the impact of having electronegative atom in methanol and chloro, or methyl chloride and methane chloride and chloroform. And hydroxyl group is an electronegative atom. It de-shields the carbon atom to 50 ppm. Chlorine, the same thing, but the OH is more strong as the electronegative group compared to chlorine. And in methane chloride and in chloroform, the larger the number of the chlorine substituent, the more the de-shielding effect of the electronegative substituent. Also, the de-shielding effect decreases by distance, as you can see in propyl chloride. The methylene directly attached to chlorine is de-shielded to 46 ppm, whereas the methyl group at 36 and the methyl group here is at 11 ppm. Olefinic carbons resonate at 123 ppm as a result of anisotropy effect, okay, and so on. Here, for example, we have observed that the aldehyde carbon is de-shielded to 200 ppm. Also, the acid carbon and the carbonyl carbon is de-shielded, okay. Aromatic ring carbon also de-shielded by the ring currents and resonate at 128 ppm. And also in pyridine, for example, we observe that the heterocyclic structures, different types of carbons resonate at de-shielded positions because of the unsaturation and the presence of nitrogen in the ring. Also, this table provides information about the chemical shift, factors affecting chemical shift. The type of the carbon, methyl or methylene or methyl, all of them of SB3, but they are differently affected, also have different chemical shifts according to the number of attached protons. All of these 4 types are SB3, but will exhibit different chemical shifts. The less the number of protons, the higher the chemical, of the more the de-shielding. Presence of electronegative atom also introduce de-shielding effects on the carbon atoms. And acetylene triple bond also observed that in acyl compounds, the chemical shift is smaller than in the olefinic case. It is not probable or was not expected because of magnetic anisotropy, a factor we discussed before in proton NMR. Aromatic also deshielded by the ring current effect, okay, and so on. Taking the NMR spectra can be acquired in two ways. First, use of continuous wave NMR. This was used in all the machines. A very simple and cheap way for obtaining NMR spectra. It is only suitable for abundant spins, in which case these atoms have high natural abundance like proton and F19, and also high magnetic moments. It is not convenient for dilute spins like N15 or like T13. This technique involves the use of monochromatic radio frequency and varying the frequency so that we can sweep or scan all resonance of interest. It was used, as I said before, in the old machines. Recently, we could obtain the NMR spectra using Fourier transform NMR spectrometers. These spectrometers use radio frequency in the form of intense, very short pulse or microsecond pulse. This microsecond pulse excites all resonating nuclei of the sample, causing them to be flipped or magnetized to high energy state. While relaxation occurs, Boltzmann equilibrium will be attained or restored. Signals will be obtained in which will be attenuated and transfer relaxation, as I said, will occur, giving rise to what's called FID or the free induction decay. Free induction decay is also called frequency domain spectrum. Frequency domain spectrum can be converted into by a very complex mathematical process into frequency domain spectrum using many computers. The time needed to obtain 100 scans by F15NMR is only sufficient for obtaining one scan by a continuous wave machine. And because the sensitivity is directly proportional to the number of scans, then this technique is very, very much having a higher sensitivity compared with the continuous wave NMR spectrometers. Pre-induction decay, as we said before, the time domain spectrum can be converted into ordinary domain frequency domain spectrum using the German computers. This is called Fourier transformation. As we said before, the number of scans is large in case per unit time compared to the continuous wave NMR, which leads to increased or improved sensitivity of Fourier transform NMR. شكرا.